It's my absolute pleasure to extend a warm welcome to everyone gathered here for today's third day of the 6-day faculty development program on integrating AI and ML for next generation electrical engineering solutions, organized by the Electronics and ICT Academy, NIT Warangal, in association with Department of Computer Science and Engineering, SRM IST Vadapalli campus. It's a privilege to welcome and introduce our esteemed speaker for today, Mr. Deepan Raj. Mr. Deepan Raj is a distinguished technical manager, data science at HCL Technologies, and a PhD scholar in artificial intelligence at the Madras Institute of Science and Technology. With over 7 years of expertise in data science, computer vision, machine learning, deep learning, and generative AI, he has played a vital role in solving complex localization and defect detection problems, utilizing MLOPs and active learning to enhance efficiency and innovation. Mr. Deepan Raj's academic journey began with a bachelor's degree in EC from Agni College of Technology, and he holds a master's degree in VLSI Design and Embedded System from Anna University, Chennai, where he actively contributed to organizing technical workshops and mentoring students. Beyond his cooperative expertise, he is also a dedicated freelance technical trainer, sharing his vast knowledge with aspiring engineers in AI, embedded systems, and programming. Currently, his PhD research focuses on localization challenges in AI, with extensive expertise in convolution, neural networks, autoencoders, and transfer learning. Thank you, sir, for accepting our invitation. Before we move forward with this session, I would like to invite our respected HOD, Dr. S. Prasanna Devi ma'am, to present a memento as a token of our gratitude and appreciation.
Yes, ma'am.
Thank you, ma'am. I also extend our heartfelt thanks to all our online and offline participants for being here today. I am sure that you will find the session enlightening and inspiring. Without any further ado, let's warmly welcome Mr. Deepan Raj to begin the session. Thank you.
Right? Yeah. Perfect. Okay. So today's agenda is going to be these are the topics we are going to cover today. Principal component analysis and some variations in it, like let's say how to use a probabilistic method on the same PCA, and how autoencoders can be utilized, the architecture behind, and the strategies which we can use to create a better autoencoder, and types of applications which we can introduce with autoencoder, because it's like the current trend, I would say, and variation autoencoder, some varieties in it, and we're also going to transfer learning, understanding some key architectures and how we can utilize those pre-trained models and train on top of that, and how do we effectively use domain adaptation, especially for a particular problem in hand. Let's say you have a pre-trained model, and how do you use this, the same model for a particular problem. So that will be the context of this workshop, or for this day actually. Okay. Yes. So if you see these topics here, we can divide into 3 sets: PCA, AE, and transfer. Okay. So we have 3 sections here. So we'll go one by one. Okay. So I would say the most simplest one would be PCA. As the name implies, principal component analysis. Okay. So principal component analysis. So what does it mean? So imagine like you have a data set. I hope you have trained many data set by this time, right? So let's say you have different numerical data, you have different image based data. The biggest problem in data sets are the number of data which is available. Imagine you have a medical data, understanding the health of a particular person, whether they are healthy or non-healthy. For example, you take some measurements like BP, sugar level, and other things. Okay, so imagine you have conducted this experiment in a very small clinic, some medical facility, and you've got some 100 to 200 data. So with that 100 to 200 data, can we train a better model with it? Is that possible in the first place? It will be tricky, right? So it's not like you don't have a sufficient amount of data to train a better model on top of that. the biggest problem which I would say is the number of dimensions we have. Imagine like you, for that particular 200 data, if you have like 20 features, let's say age, BMI, pressure values, likewise, if you keep on increasing the dimensionality of the particular data, the model finds a little overwhelming. Imagine like if I ask you to study 20 subjects in the semester, would that be possible? Very tough, right? So again, studying 6 subjects is always a tormenting effect for us, right? Which means that how do I effectively, take this much amount of features and with a limited data set, how can I train something on top of this? So this is a biggest challenge, especially for numerical data, right? So this dimensionality is a curse. You can't expect the model to understand. Starting. Okay. I've already joined. They are collecting.
Continue, sir. We'll talk to them.
Oh.
Edinburgh, Oxford. The wireless device is ready to be tested.
All right. Yes. Let me show an example. Just to realize what I'm trying to say. Let's take this example. Okay, so this is one of the data set which we have. This is basically understanding whether a particular mobile phone is a hit or a miss. Based on the specifications. We can people from this I guess from the website Mobile 91. They kind of gather this information, the technical specification, and how people like this particular mobile phone. Okay, so if you see this data, right? So I scroll down all the way up to down. You see like you have 110 rows, just 110 instance of data, which means that you have just very limited data to consider to understand whether a particular mobile phone is a hit or miss. And if you see the number of columns which you have, the features which I'm talking about, right? It's basically columns. Every column represents here are basically one feature. SIM type is a feature of a mobile phone, right? So we have aperture, GPU access. Likewise, if I scroll all the way to the right side, you have these many features, roughly around I would say like 20 to 22 features. So for 100 row data set, and we have 20 columns to start with. So the biggest problem is like the model has to find patterns on all these features, because let's say you push it to a machine learning or a neural network, right? So what it has to do, it has to take all the features, it has to understand every data in hand, and it has to find the patterns in there, like what every feature does, like how we can place the component or the values within it, and how do I differentiate these things. So these all the mechanism which enters inside a network, right? So it has to find the unique patterns that represents this particular class, something like that. And imagine if you have multi-class problem, it's a binary class, 0 and 1. Imagine you have a multi-class problem with this many columns. Just give it a try. Saying train this kind of a model, you will definitely see it's not going to be a fruitful result, because the biggest problem is the number of dimensions. So when dimensions are very high, it's going to be very tough for them to understand. Now, what are the additional steps which we can take to make this better? You have a very limited data. Yes, you can go and collect more such samples. Maybe that's one thing to go. But again, not every data is can be expandable in nature because of the veracity it gives. Which means that we are forced to use that limited data, and we have this many features with us. So any strategies which we can apply on top of this, rather increasing the number of data, what else I can do? Any wild strategies? Okay, I'll just spill the beans in this case. Okay, imagine you have 20 features, you have 20 subjects to study, and obviously no one can do that in a single semester. What do you do in that case? Study all the 20 subjects, or take some 10 subjects out, let's deal that next semester. Do that, right? So we just chuck away a few, you make sure all the important and non-important, you fix those things. You say, okay, these are some few easy subjects which I can easily crack. These are some tough subjects, I cannot push all the tough subjects to next semester. I'll take few this time, I'll take the next one, something like that, right? So what you will do, you will try to segregate the subjects. Right? You try to understand, okay, which is good, which is bad. You try to segregate it, and you focus on few subjects, which would be decent enough at your standpoint. Okay, so we have done something, at least to start with. You have passed 10 subjects. Losing 10 subjects is another end, but at least you have done something with those 10 subjects. Very similarly, what if I can remove few features out of it? Is that a possibility? Yes, it's our data set, right? So we can decide, you can do many different plottings. I hope you have tried this, EDAs, exploratory data analysis, right? So you kind of understand how these data are represented, how it is placed, whether it has a lot of variance or, it has very less variance. You kind of, do these kind of exploratory data analysis. You plot these contents onto a graph and see whether it is good or bad. If it is very bad, if it is not having good linearity representation, or let's say it has having a lot of variations. Variations in the sense you have a sim type. What's a particular sim type? Usually 0, 1 and 2, right? But in this case you have even 4 sim types. And in many cases the data would be very scattered. You can't expect a model understanding the standby time of this particular battery, which can range from 0 minutes to 1000 minutes. It's too high of a range, and all the values which you see might be liked by the people as well because of other features which is built. Which means that there is one thing I can try to see which is highly variant. I can remove those parts. I can simply remove those features, reduce the number of features so that I can concentrate little good on that. That's one. Or else I have to stick with the entire content. Try for a better algorithm. And again, no matter what algorithm you use, right? It will be very tough for the model to bring down. So again, if I remove those features, yes, that's a good strategy. But what if the features are very important, which you might not know, even though you did all those EDS and stuff. Somehow, that feature is kind of related on a multi-dimensional space. When it interacts with other features together, it puts the model into a better position. We can't, especially say that unless we do some mathematical, experimentation on that. So in order to avoid this particular problem, in order to make sure we utilize all the features effectively, making sure all the features are used, but in a way the model can somehow grasp the contents, we created a concept called principal component analysis. So very simply put, the problem which we were talking, right? Yes. The problems. Hello. In game. The problems, right? Which we are talking about. The number of features, lesser data. All these stuffs will be the problem. In order to reduce the features, we use principal component analysis. That's all. Now what does it do? How does it reduce these features? So that's what we're going to see. Okay. So if you see, right, so it's an exploratory technique used to reduce dimensionality of the data, blah blah blah. So basically we are trying to reduce the dimensionality of the data. That's like the number of features we have. You're going to reduce that. How you're going to do that? You're going to apply some mathematical strategy, making sure you're not just going to remove that feature just like that out of the picture, but you're going to combine some features together to do some, different, ideally, in a way, you kind of find a different medium of data that has all the features embedded inside it, something like that. So imagine, let's take this example. Like you have some data which is scattered like this. You see, right? So these are some X dots which you see. So these X are basically your data. Okay, imagine these are your data, and what you do, I just try to find the the variance of it, like how much variation does it have, and what will be the width of my variation. I find to see, this particular axis. See, like, okay, this is where in the entire data is present. Maybe I can draw a component line like this, and very perpendicular towards it, I draw another line. That's called PC2. Okay, I draw PC1 that moves along this entire data that shows the maximum variational axis. Okay, so this is my data, and this is the maximum variation happens because this is the variance which I get. So I try to draw a line that is inside this particular data. Okay, so what I will do. Okay. Imagine, like, this is the data points which we were talking about, right? So what I will do, I'll just calculate the maximum variation in this axis, like, in one axis, and the maximum variation from in this axis. Which means that this is one variation and this is one variation. So based on that, I'll find which has the biggest variance, which has the largest variance. I'll try to draw a component along that particular axis. Okay, that's point number one. So what else I will do? I'll just draw a perpendicular line, or basically, anyways, whenever you have a data in two-dimensional, right? So one is having higher variation, another will have lesser variation. So if you draw a perpendicular line towards it, you get the second axis. That's all. So you draw the first axis that has the data within it that has the maximum variance, and you draw the second line which is perpendicular towards it. Obviously, that's going to cover the remaining portions of the variance. Okay, so that's how you do it. And now, what this line represents, what this is all about. So I'm just trying to, convert this entire data into one component line. Imagine if you have two features to start with. I can convert the two features into one feature. I can just use this PC1 as one singular feature that captures the essence of both the feature 1 and feature 2. Because this is, imagine like this is feature 1, your area is feature 1, right? And this radius is feature 2. I just plot it here. I can draw a component line like this. That basically, converts this two feature into one single. That's the strategy behind it. You got the idea, right? So instead of me, removing a feature, I'm just trying to combine these two features together, but in a more effective way. I'm not just going to add or multiply or do that stuff, because if I do that, the tangibility will be like very high. I'm not sure like which data contributed to this arrangement of numbers, right? So in that case, I can make sure this particular component is calculated in a way where it captures the essence of both the features together. Now, how did this happen? You can use eigenvectors and values. You can just do a simple calculation with eigenvectors and values, and get this maximum variation. So with that maximum variation, you can place the axis on top. Very simple. Okay. So this is the most fundamental, concept behind PCA. So what's the problem behind? What's the problem which you're trying to solve here? We have a data that might have a very limited number in terms of instances, and we have more features altogether. So we have a lot of features where the model can't digest, understanding these many features at the same time, to extract information, to find the sweet spot between those feature maps and things. Which means that I have to find an effective way to reduce those features. That's point number one. But making sure those features contributes better than the original data. Because again, if I reduce these features into one single feature, and if this is not contributing towards my learning, then there's no point in doing it. Right? So I have to make sure the feature which I'm just combining or which I'm just fusing it together should be better of both the worlds. If I have feature A and feature B, imagine like this area is feature A, this is feature B, right? So imagine this PC one should be better off both these worlds. So it should have better representation of these two features together. So which means that when I use this data instead of this A and B, I should be getting almost at least like the same value towards it. Yes, there can be slight reduction in terms of values because obviously two feature and one feature always a huge difference. But we have to make sure we have those values in terms of reduction to be as minimal as possible. Okay, and again, PCA plays a vital role in many areas, not just some numerical data. Yes.
Meeting is started.
Started, no? Okay. You have to join it again.
Oh, so
Share my screen. Yes, so coming back, this is how PCA works in the first place. So I'll just quickly summarize this. So PCA is called Principal Component Analysis. You have a data set and you try to reduce the features so that the dimensionality can be reduced. The model can pick better reasoning out of the data. I use PCA to reduce the dimensionality using eigenvectors and eigenvalues, just calculate the variations of with the data and try to place the axis on top of it. We get it done. So based on the axis, you see like which has the bigger variation. So you take that as the actual component. Yes, you can also take the PC2 as well, but again, there's no point in using two features against two. So it's not like it's a good ideal way to do this stuff. So you can use one feature for two data, or you can even have a multi-dimensional space. You have four features. You can place one feature as well. So you can increase the number of features as well. It's not like you have to use only two features to get one feature on top. You can also have 5 features, include as an input and take one feature as an output. That's how PCA works. So it tries to reduce the dimensionality. Reducing the dimensionality makes the problem much more easier for the model to solve. Okay, that's one. The next thing, apart from PCA, we have another concept called probabilistic PCA. So yeah, as we know that PCAs level we have very different varieties, and one such variety is this probabilistic PCA or PPCA. So what does it do? As the word probability implies, you can get some probabilistic distribution with the data which is given. Okay, instead of me using some eigenvalues and vectors, I can use a probabilistic distribution to understand the data distribution better. For example, where this can be useful. Not many times you have the entire feature with you. Sometimes there will be a lot of missing values. Sometimes you might not have captured all those important values in that particular data. Because of that, creating a PCA will be a little tough. Imagine you should have a variation between 0 to 100, but the data which you have captured is between 20 to 80. Which means that you didn't capture the entire essence of the Yes. You try to what I was saying. Yes. So you try to utilize this methodology to find the missing values in a better way. And yes, it can also provides a generative model for the data. Okay, for example, you feel like this might have some more values in it, but which was not captured properly because of the number of data I have. So I can use this probabilistic PCA to find a distribution. I can use a Gaussian distribution basically. You know what is Gaussian distribution, right? Uniform or a normal distribution which is here. So you have a simple bell curve, right? So that gives you like 99% of distribution for the plus or minus 2 other standard deviation. So the very standard Gaussian distribution is also fine. You can use a probabilistic method to do that. But usually what we do is like you use GMM, Gaussian mixture models. Instead of using just the Gaussian distribution, I can use a Gaussian mixture models and try to find the entire distribution of the given data, rather not using the actual data itself, but I use a GMM approach to find the missing values as well. Before me creating this principal component, I try to find a distribution of all the possibilities of the particular feature, and then place my PCA on top. So that's how this probabilistic PCA works in the first place. Simply put, if I go back to this graph, you see here, right? So imagine like this particular region, I have data, but what if I might have some data here as well, and here as well? There can be a possibility, right? So which we might not know for sure. So this GMM, right? So this Gaussian mixture model, what do it tries to form the distribution for this data and tries to find the intermediate points, like intermediate values, something like this, and find all the possible combinations in terms of a distribution. And once I get this distribution, now if I try to find the eigenvalues and eigenvectors, I can have a better variation, correct? The variance will increase now. Instead of me just applying on the same data, I can apply some probabilistic method. GM is one such methodology. It's not like you have to use that. You can use any different methodologies to improve, to generate a better content or the better content for the feature, and then apply PCA. You will have a even more stronger variations. Or another way around. What if I have data here? Instead of going this axis, let me go in terms of area. I have some values here. So what happens? This variance will increase. The principal component 2 will have a huge variation than the principal component 1, which means that this will become PC1 and this can also become PC2. Okay. And again, general word of advice: you use a PCA to somehow distinguish the features in a much more better way. Okay, if you have many overlapping features. Okay, for example, you have many overlapping values for these two features. I can try to distinguish those in a better way using PCA, but probabilistic PCA can't do that. Okay, it tries to add more values towards it. It tries to generate some more values towards it, and then place a PCA, which means that you can't expect probabilistic PCA to work better for all the data in hand. That's one. And again, yes, there comes times when you feel like the data are missing. If you feel like the data are not much good enough for a model to train on, that's where they can use a probabilistic PCA. Or else you can go with a simple PCA. And again, it's not like you have to use PCA every time when you have a huge diverse sampling. It's always better to see like how the model works with the given data. If it works fine, leave it. If not, if it's not working properly, then apply different strategies like use PCAs, PBPCAs. You can try different methodologies on top of it. What else you can do? Instead of probabilistic distribution, what else I can do on this point? So all you have to do is reduce the number of features, correct? So one idea is like you use a probabilistic method, you find the maximum likelihood estimation and find the principal probability. That's how you do it. But instead of having a probabilistic distribution, I can create a different concept called SMOTE, SMOTE. Okay, that's an augmentation approach. Okay, so I'm just giving you some open points. It's not like you have to indulge with this methodology alone. Like, what if I use a SMOTE technique? Improve the data just like that. I'm not going very deep into that, but SMOTE is a way where you can augment a lot of data points. Okay, for example, you have very limited data set. They want to increase more features, or not like more features, more instances. As I was saying, right? So you have 100 features with you. Sorry, 100 instances with you. And you have 20 features, and you feel like those 100 instances are very less. If you see this data set, you have how many rows? You have just like 110 rows, right? So you have this 110 instances. What if I use this SMOTE technique, and increase it to 200 rows? That might have a lot of distributions, right? And what if I apply a probabilistic distribution on that? Use a GMM on top of it. I get even more better concentration. What if I apply PCA on top of that? These are like food for thoughts. You can just give these, at that. All you have to do is make sure you create this principal component in a much more better way. And how you can do that? When you have more supporting data, when you have more supporting information on that particular feature, the PCA can be even more better. So in order to do that, you increase the data, and if that's not possible, use a SMOTE technique or use any approach, increase the number of data, and then use a probabilistic method. You also have a many different approaches inside probabilistic approach. Okay, you can use many different distribution methodologies as well, making sure you have sufficient data to deal with. And once you have sufficient data, PCA is a piece of cake for us. That's all. Got it? Yes. Key takeaway. What's the key takeaway when you have to use this PCA? When you have more features to start with, and if the results are not fruitful enough, you can use PCA. But if PCA is not giving you a good result, what you have to do? Because obviously you should have some other ways as well. It's not like if PCA is not giving you good results, you should not be taking the data set on again. Okay. You have to see like what else you can do. What else you can do? You can apply PPCA, probabilistic PCA. That is also not working great. Dig down the data. See like which data is like performing really worse. It's like having huge variations inside it. Maybe remove that feature, or use a SMOTE technique. Just Google about SMOTE. It's like very straightforward approach. but again you have a lot of variations inside code as well. Increase the number of data, and then apply a probabilistic PCA on top of it. Make better features and then train. So these are some strategies which you can apply to get better results. So at the end of the day, we have to get better models to perform. Imagine you have your face unlock, right? I cannot say that you have a feature as face unlock, but it won't work every time you use. Will you use that feature? No. Which means that whatever data is thrown at us, you have to make sure you get the maximum juice out of it. You can go as high as possible. Try to get some benchmarks. See like who has used this data set and what's the maximum accuracy they have got. Can we attain to that level? Till that you can try different approaches, and that's where a new discovery can happen. Okay. So these are some strategies behind. Hope you got an idea about PCA, right? Any doubts or clarification? Okay, I'm not going very detailed into mathematical part because if I go there it's going to be a little boring. So I'm just giving you a high level idea like how this PCA works. But if you want to understand the mathematical part, just find like how you calculate an eigenvalue vector for a given data, how you can calculate. So if you know that, that's what you have covariance calculation. So you have some steps as well. Okay. So if you do that, you can easily understand the PCA. That's the only mathematical part which you have to understand. And again, you have probabilistic additions between it, so you can also add that. That's okay. So we'll see some implementation on this. Okay. So you have systems with you? No. Okay. I'll just show you the code first, and I'll give you some time. You can just give this a try. So we have Colab. I hope everyone knows about Colab, right? Yes. So let me open Google Colab. So go to Colab and go to File, click Open Notebook, go to GitHub and search for the repository named Deep Learning. Okay. So all you have to do is go to this website colab.research.google.com and then go to File, click Open Notebook, right? And inside Open Notebook, just go to the GitHub tab, right? Search for the handle name Deepan Raj M, and go to the repository name machine learning. Okay, that will be the repository. And if you scroll down, you can see a program named PCA. Okay, you can see a program named PCA, which we are going to use. And you will also have other programs like PPCA. So there will be like 3 programs which I'm going to cover for this principal component analysis. So one is PCA, another one is probabilistic PCA, and also PCA versus PPCA. So like, which gives us better results. So we can do some basic comparison between like how things work in the first place. Okay, so these are the 3 programs which we're going to run. So I'll just teach you first, and then we can start with your. First, we'll go for PCA. So if you click this PCA program, you can will be going into this. So here, like I'm not training any model here. Okay. So the model training will be done in the third program. First, I'll just show you like how this PCA can be done for a given data. Okay. So if I show you the imports which I have, I'm using pandas, numpy, matplotlib. I hope you know these packages, right? So pandas we used to load data, manipulate contents into it. NumPy is a mathematical library. You can do a lot of mathematical calculation with it. I'm going to load a breast cancer data set. It's not just images, it's just some readings of the cancer part. And you have a standard scaler and you import this PCA. So PCA is a part of scikit-learn. You can directly use scikit-learn library to import this principal component analysis. Okay. So first things first, I'm just going to run these, import these packages. Yeah, so once it is imported, I'm just going to load the data set. Okay, I'm going to load this cancer data set and just going to print like what are the features we have. So mainly like we'll be having, I'm just going to take the data and the features. Okay. Because I'm not going to take other information, so I want to know the actual data, the entire data. From the data, just go for the feature names. So just want to see like what are the features I have. Okay, and then I use standard scalar method so that I can scale all these values. This is very important because every feature will have its own scale values. Okay, it's not like one feature will be measured in terms of centimeter, another feature would have been measured in terms of meters. When you see in terms of number, the values in meters will be less, but the values in centimeters is going to be high because 1 meter is equal to, or some bigger values, right? Which means that you can't use the same or a different scale when you do a principal problem because you have a very huge variations on top of it. Which means that I have to scale these values to make sure I have everything in a normalized fashion. Okay. So all the meters will be converted to centimeters so that every values will be centimeter. I'm just giving an example, but basically you just have to normalize this into a standard scalar value, so that when you try to apply this PCA, right, so you will get a better understanding of the data. But if you have different scales, that might put the data into a different understanding as in the first place. Okay. So in order to make sure I'm using the standard scalar to reduce the variations inside by normalizing the data, and then I'm just transforming into the data frame format. Basically like scalar data TF will have all the contents in a standardized manner, and then I'm applying this PCA. Number of components which I apply is 2, so you can also increase the number of components here. That's up to you. If at all you have more features and you want to have at least like 5-6 features on top of that, then go for a bigger component value. Okay, and then you just call the command pca.fit the entire data set towards it. So this will basically analyze the data and then transform it to values. Okay, so this will fit the components on the data, and this will basically transform the values so that you can get the values and just copy it on top of it. Let me just run it, just see like what really happened in the first place. So like these are the features we have. Okay, so the features which you see is your mean radius, mean texture, perimeter, mean area, smoothness, compactness, concavity, concave points, mean symmetry. So these are some features. I have like some more features like mean fractional dimension, worst areas, worst texture. So like I guess there are many components inside it. Okay, so roughly 30 columns of data. Okay, so 30 features to start with. Okay. So the number of features you have 30, the number of features you have 569 crores. So obviously the distribution is going to be like variated a lot because it's a medical data. Because especially for medical data, right, you can't expect it to be like having lesser variation. Definitely have a lot of anomalies because not every person reading will be the same. So you'll have a very huge variation between the data, and it will be always tough to have a same margin between it. So that's how things will go. So I take all the points and try to form the PCA. So now these are the two PCAs which I got. Okay. So I place the component and I apply PCA and I transform it. So this yellow point represents the component 1, the darker point represents the component 2. So based on all these dimensions, let's say I have 30 dimensions of data, right? So from the 30 dimensions of data, I'm just converting into fewer dimensions. So I can increase the dimension as well if at all required. I can just go and use the number of components as higher. But I cannot accommodate here to show you all the graphs towards it. But you can increase the dimensions as well. Okay, because increase the dimension will give you more features to start with. Because as I told you, it's not a wiser option to convert the entire data into just 2 features. That might not capture the entire essence of the data, because sometimes the variations in this case, right? So in this example, it's very simple. You don't have a variation, so very less data. So just this much amount of data is only given. But what if you have a lot of features like this? So like here, all the way up to every places. And imagine this is a multi-dimensional space. It is having all the data different dimensions. So the variations can be very high. It's not like you're gonna have very small number of data like this, which means that the variations is going to be very high, and not to find one component for the entire variation is going to be very tricky, because imagine your variations like this, this and this. Okay, so this variation is, for example, this is 10 pixels, and this variation is 11 pixels. Now this 11 become PC1, and you have one more dimension that you have 9 as a variation, because on a third dimensional scale. So what happens now? We just consider only this PC1 and PC2. We might neglect PC3, which is also a good value, because 9 is also a good variation compared to these points, but we neglect that because we just forced to have 2 features. So that's why if you're going to do that, make sure that the most perfect way to do is, take the column which is very important, or which is of least importance, that has very less variations. You have correlation method. You can understand how the model correlates for a given features. So you can take those less correlated data and apply PCA for that less correlated data. So you can reduce the number of less correlated features into one single feature. That's fine. But you have a highly correlated features with you. But why do I need to remove those highly correlated features? Because that helps my model to learn better. I should not be removing those. I have to make sure those features are intact. Okay, but here I just blindly run the PC on all the data, so that's why I get something like this. But again, this data are somehow linearly separable in nature, agree? So it's somehow separated. So maybe I might get a good opportunity to train better models on top of it. But again, as I told you, don't go with more reduction. Have a very decent number of reductions. Okay, that's fine. Second program, you have PPCA, that's probabilistic PCA. Very similar to the previous program. Okay, there will be no variations inside it. The initial steps are the same. Only this area is going to change. Okay. You take a number of components. You use this Gaussian mixture approach. You take the GMM on top of it and then sample it. Okay, because you have GMM will have different latent variables. I'll come to latent variables at some point of time in the upcoming sessions. But you get the GMM values, and from that you can get the how many principal component you want to extract. You can extract on top of this, because this will fit the line very similar how we did it. Right? So this GMM will accept the number of components and find the covariance type as full, which basically takes all the covariations into account, and then it fits the model and gives you this. Which means that it's like a single line implementation, but the component which we talk is very big. But again, since it is scikit-learn, right? So it's like a very easier way to do it. So if you see, right? So inside scikit-learn, make sure you use a Gaussian mixture just like that. Okay. So you do that, you get it like this. So let me run it quickly. Note the data set. Everything stays the same. Only this GMM part is going to be little different. Okay. So we're going to GMM to get things done. Yeah. So this was the previous run. and I'm using the same data set. Okay, I'm not even changing my data set. I'm using the same data set and doing this. Let's see like how it works. So you see, right, when you see this data, this looks very good than this, right? Correct? It's entirely scattered here and there. So that's why I told you, probabilistic PCA will try to use a GMM approach to increase the number of distributions, generates a lot of patterns. Sometimes it will be very helpful to find the missing out values. You have a huge gap in the data. Those are a lot of missing values. Then yes, probabilistic PCA will work. But again, as I told you, it won't work every time. If it works every time, obviously like, there should be a flaw with it, right? So these are areas which you can use. It's not like you can use it for every data which you can use. Okay, so that's how you have to do. So you see these projections, you see like how these projections are, and then decide whether it is good or bad. That's one thing. And finally, I'm just going to train a model with this PC and BPCA. Okay. So for this, I'm going to use this MNIST datasets, one of the famous datasets, like you have image. Okay. I hope you know about MNIST. I'll just show you how this dataset looks like. So this is how the data looks like. Okay, so you have an handwritten digits varying from class 0 to 9. You have digits from 0 to 9, so which means that you have 10 classes to start with, and these are the images which you have. So you have a huge sample rate. So what I'm going to do is, I cannot take the entire sample rate because calculating the GMM or calculating the PCA for the entire data will take a lot of time. So what I'm doing here is, I'm loading the MNIST data set. Okay, I'm loading it, and from that loading pattern, I'm just taking the X train and Y train, the test size of 90. So from the same X train, Y train, I'm just splitting 90% as test size and 10% as training size, which means that out of this entire X train, X test, Y train, the training data, I'm just taking the 10% data for my training. Similarly, for the training set also, I'm doing the same. So basically, I'm just reducing the number of data which I have. Okay, because the number of samples which you see for MNIST data is like 60,000. So I cannot go along, run for 60,000 data. So it will take a lot of time. Okay. So I'm just going to reduce it to 10%, which is roughly around 6,000. Yeah, right, somewhere around 6,000 data. So I'm going to use 6,000 data for training and somewhere around 1,000 data for testing. Okay, so that's what I've done here. So if you see the imports, so all are the same till this point. So I have an MNIST data set. I'm calling these operations to train my model. I'm going to use a simple neural network to do this. That's all. Okay, so I use the sequential dense methods to train models and do stuff on it. Okay. So let's import all the packages. I just load the data set, flatten it and normalize it. If you see, right, so I'm just flattening this into one single, because it's an image, right? So image should be having two-dimensional data. I'm just converting into one single line so that I can use it on my PCA. And again, PCA, in order to do PCA, you have to make sure all the data in one dimension. Okay, you cannot have, yes, you can have multiple features, but you should make sure the data is in single dimension. You should not complicate things down here. So you have to make sure you do that properly. So I'm just flattening the data from both this X train and X test from 2D to 1D dimensional data. And then I use the same standard scaler fit the data so that all the pixel points are normalized in nature. So this is a standard approach which you can use. It's not only for the numerical features that you have, even for images you can do this. So once the data is fixed down, apply PCA, number of components, give the train data, get the test data as well. Similarly, I can use a GMM to get the data, plot it. First plot, see like how it is, and then start training the model. So I have the data set with me, and I have to convert this labels into categorical, because my neural network accepts categorical input. That's like basically one hard structure, right? So like something like this. Instead of 0 and 1, I'll be having 0, 1 and 1, 0. If you have 10, if you have 3 classes, it's going to be like 0, 0, 1, 0, 1, 0, and 1, 0, 0. So this is called one hard encode because your output neuron will be number of neurons, only one neuron will activate at a point of time. So which means I can have to convert these numbers into one hard encoding. That's why I'm using this categorical method to convert all the values into one hard encoding and then apply your simple neural network where I'm gonna have 128 tens followed by 64 and followed by 10 because these two are your hidden layers. The final layer is going to be your output 10 neurons. Okay, that's all. Because you have 10 classes, you have to have 10 neurons. Okay, so just compile it and then train them on. So during this training process, I'm going to train for 3 times because one is going to be raw model because I want to see like how the raw model performs without any PC or PPC applied and how a PCA works and how a probabilistic PCA works. Okay, let me run along the way. So like I'm just gonna load the data set. Okay. Let's just load this one. Actually. Okay, you load the data, apply PCA. And after you apply the PCA, right, you should be getting the the actual components. Obviously, the components will be a little scattered, right? So it tries to allocate as many components on top of that, and these are basically the number of classes you see. Okay, so we have many different classes within it. So it tries to allocate these components for it, and you see that. So this is having some elongated circuit. This is like more of a round figure. But let's see, after this conversion, let's see how the model performs. Let's train with the raw data, 10 epochs. Let's see the result for that. And you can see the results are pretty good because you have a training accuracy of 19%, validation accuracy of 93 for a very small data because I've just used only 6,000 data for training and just 10 epochs. With a very small neural network, this is far better result. Let me use a PCA. See how it works. Now the data you see, right? So extend PCA and white train cat. So extend excess PCA. So these two are converted as PCA values. Now you see the result. What is the value you get? You get which is very less. So this is very evident that the raw data performs better. I don't even want to convert it to a converted PCA values. Now let's see how PPCA works. The same number of patches and everything. Let's see how this works. What does this one? Okay, the training is 68%. What about the validation? It's just 10%. Right, so 10% for PPCA, 35% for PCA, and 93% for raw data. So what does it put us into understanding? The features which you have, especially since there's images, right? So the values will always be between 0 to 255. So obviously the features plays a vital role for the image data because every features, every pixel. If you remove pixels, there is a good possibility you might remove the understanding of the features in the first place. So applying a PCA on images or some data or not every time a PCA works. Okay, you have to make sure where and how to use it. But yes, there's no harm in applying PCA and checking it out because it's like matter of time to train the model. But compare the results, see which gives you better values, and then P start. And again, probabilistic PCA, I told you it's not applicable for every time because it's an image data. You might be having a very lesser missing values. Because the values are well defined between 0 to 5. It's like a pictorial representation. So for that, definitely there will be lesser missing values. So if you don't have a missing value, then don't ever go with PVC because it won't give you any good out of it. It's just going to bombard with more irrelevant data on top of it. So make sure that's what happens. Okay, so where you can use PVCA? Whenever you feel like the data are missing, there's a lot of missing and the model is not performing really great, that's where you can apply
GMM to do it. If not, apply a simple PCA. And again, before you even train a PCA, just see like how the raw data works. Set up a benchmark, and then start dealing with it. So that's how things has to be. Got it? This is clear? Any doubts or clarifications? You can just give this a try. See like if you get some results on top. You can just try with any data. So all you have to do is just make sure your data is loaded properly. Okay, so your data is loaded properly, and you apply this standard scalar method to scale the values, and then apply the same PCA. Okay, so try with any data set. You have two programs here. Okay, so you have PCA where I've used the numerical data. Okay, so where I've used the numerical data to start with. PCA with PVCA, I'm using an image data. So you can I'm just showing different variations like how to utilize PCA for different modalities. So you use these two scripts to start with. But if you feel like you want to use some of your own data, right? So take this particular program, for example, let's take this one. So this is a simple, okay, let's take this one. Let's take this logistic regression program. Okay, so you have this data set, this mobile clean data set has been applied. Okay, so just go to the same space, just look for this logistic regression program. Try applying PCA for this logistic regression code, see like how it works. Okay, so these are some variations which you can try out and see like whether it works or not. Okay, so I'll just give you 5-10 minutes to work on this program. See like whether you get some results. If you have any doubts or clarification, do raise your hands. We'll come there. Okay.
இந்த மாதிரி போயிட்டு நீ ஜிம்மு போனாலும் நீ ஜெனிக்கேட் எடிகேஷன் இல்லைடா வெயிட் அடி வெயிட்டுக்கு மிஷின் உடச்சிடும் பைக் சொல்லி